Hi folks, welcome back. We're still dealing with polygons here. We're going to talk about a few theorems of polygons in general. We can classify polygons based on some of their characteristics. Those characteristics primarily are the sides, or specifically the side lengths, and the angle measures. And these are some of the ways that we can tell or we can describe a polygon. So for instance, this would be a triangle. Okay, that would be a triangle. This would also be a triangle, as would this. Okay, and this is a kind of a special kind. We call it a right triangle. So these would each be triangles because they have three sides, three vertices, three corners. A vertex is the corner here. So maybe label that. So this would be a vertex. It's where we usually name them. Vertex. The plural is vertices. Plural of vertex is vertices. Okay, so those would be vertex. Those would be the vertices of this triangle, 1, 2, and 3. This would also have 1, 2, and 3. And this would also have 1, 2, and 3. Now beyond that, we can also classify these triangles relative to one another. I can say that the sides of this triangle, the sides of these triangles, let's say they're all the same. Let's say they're all the same length. Let's say that these are each 9. So that's 9. That's 9, that's 9. And the descriptor I can use for that is equi, again from the root for equal, equilateral. Literally means equal sides. They're equilateral. So I could call this an equilateral triangle. Okay, and this one, well, it looks like these are a little bit shorter than the other two. So that would not be equilateral. This one's definitely longer, so that would not be equilateral. But if all the sides are the same length, we can call them equilateral. So I could say this is an equilateral triangle. Similarly, we could talk about these angles here, maybe that angle and that angle and that angle. And let's say that those are all the same. And if they're all the same, and there's 3 of them, they have to equal 180 because it's a triangle. The sum of all angles in a triangle are equal to 180. So that means that each of these has to be 60 degrees. 60 degrees there. That has to be 60 degrees there. And that has to be 60 degrees there. And if they're all the same, I can say they're angular. They're all the same angle. Okay, so again, equi means equal. Angular, that's dealing with angles. Lateral, that's dealing with sides. So we've got all the sides are equal. Sides all equal. And here we've got angles. The angles are all equal. And we actually have a special term for something that's both. So if these are both, that's both equilateral and equiangular, we call that a regular polygon. Regular. So if it's ever describing a regular polygon, it's nice because all of the measurements of the angles are the same. So if you know any one of them, you know all of them, and all of the lengths of the sides are the same, the sizes of the segments that make up. So this would be both. So this would be both equilateral, and equiangular. And that's kind of a special classification. Not too many polygons, or many more polygons are not regular than are regular. So something could be equilateral, but not equiangular. Especially when you get into the other shapes, we can deal with that. Something could be equiangular, but not equilateral. Rectangles are a good example of that. They have 90-degree angles, but perhaps the 2 of the sides are longer than the other 2. But if it's both equilateral and equiangular, we call that regular. Now there's one more fairly straightforward classification scheme that we talk about here, and it doesn't work with triangles, but it works with, let's say, pentagons. So I could have a pentagon that looks like this. I could have a pentagon that looks like that. Now, how do I know it's a pentagon? Well, it's got 1, 2, 3, 4, 5 vertices, 1, 2, 3, 4, 5 sides. So this is a pentagon. Penta for 5, pentagon. But I could also have a pentagon that looks like this, right? I could also have one that kind of looks like an envelope, but basically I'm taking these sides, and instead of pushing them up away from the shape, I'm pushing them down into the shape. But this is still 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is still a pentagon. Still a pentagon. Okay. But these pentagons are different. They have different properties, and in fact, we're going to find that this is kind of a nicer one to play with. This gives us some issues, but we have this term. We have these terms. We can say that this is convex, and this is concave. And maybe I'll do a video on the specific definitions of this, but the way I think of it, and sometimes people find this useful, is if I were to take a bucket, of water, and I were to dump it onto the shape, right? Dump it onto the shape. If it were convex, it would all the water would run right off the side and drip and make a little puddle there, okay? But if I were to take that same bucket of water, and I were to dump it out into a concave pentagon, well, it would flow out, and okay, maybe some of it would spill over there, but it would start to accumulate. It would start to collect water in at least one of the pieces, or between two of the sides, or maybe more than one of the sides. So concave, just like we use it in normal terms, has a depression or a divot, some kind of infolding that would allow it to hold water. So you can think of it kind of like a trough. Whereas convex is more like a bump, where the water is always going to be running off of it, no matter how you do it. And the trick here is that you want to be able to turn. This has to be true for any direction that you turn the pentagon. So if I were to rotate it, this pentagon here, and the one on the left would still reflect. It would still deflect all the water off the sides. But here, well, I don't need to rotate this one, but it would collect water in here. So that's concave. And there's a more formal definition that maybe I'll do another video on, but these are the basic classifications that we have. We have convex and concave. Together we call this concavity. And we also have descriptors of the angles and the sides, and if together we can call this regularity. So you could describe a polygon based on its regularity, about whether its sides are the same or its angles are the same, and its concavity, about whether or not it has any infoldings. Are all of the angles pointing outward from the body of the polygon, or are some of them pointing inward?